Okay, you're asynchronous. One more day of asynchronous. Hopefully we'll see each other tomorrow. Okay, sum and differences of functions. Literally, sum as in a plus and difference as in a minus. There are a couple of things you will see. The point of chapter 8.1, actually, the whole point of chapter 8 is essentially learning a little bit more about notations. In other words, how do I express, or how are some different ways I can write the addition of functions, and how are some different ways I can write the subtraction of functions? You will see that I give you a new notation, just a special different symbol, and we will talk about what it means, okay, in terms of its graph, in terms of visuals, in terms of, how about I write this? Visually or graphically, right? In terms of things like domain, and just a bunch of other things, right? And understanding its meaning based on the mathematical language that you see. Just learning how to speak this new language, okay? So let's talk about this. Consider the functions f of x and g of x. Label each function correctly. I'm going to assume that you know how to label linear equation or linear lines. Linear lines, wow, redundant. Plus 2 recognizes that the y-intercept is a 2. Minus 1 recognizes that that's a 1, negative 1. And I think that's the simplest way to do it. Some of you might just look at the slope instead. The slope is a 1 and the slope is a 2. Clearly, the red line is steeper, and therefore, that's f, and the blue line is g, whichever way works for you. Now, what does it mean when I am adding the two graphs? Well, that's like saying f of x is another way of saying what is the y value when x equals something. So it's like saying, give me the y value of the f function and the y value of the g function. That is the sum of f and g, right? So that's what a new function is. That's what the new function is. We are going to have h of x being f and g, which is, again, the y value for the f function plus the y value of the g function. So yes, I don't do this yet, but let's just get into the meat of it before I do the extra details. On this graph, I have provided for you some key points that are going to be added together. So let's bring this back up. And let's bring this back up. All right, let's do this. So when x equals -2, the y values are 0 and -5. If I were to add 0, so that's 0, in other words, sorry, 0 plus -5, what is that going to equal to? -5. So using a different color, how about what comes up nicely? There's blue and red on the green already. Let's use green, okay? That is going to be my h of x. Let's move on. When the x value is a 0, I have 2 and -1. Add those together, I'm going to have +1. I also gave you when x equals 0.5. 2.5 and 0. When I add that together, it's 2.5. Ooh, when x equals a 3, I have a y value of 5 and another 5. So 5 plus 5, it's way up there. I did not draw it. Of course, I make this mistake. Let me zoom out just once, which means I have to shift everything once again. But everyone else, would you label where y equals 5 is and plot it in? So let's see. I'm going to bring this back down. I don't need this. And 5, -5, 1, 2.5, 5 plus 5 equals a 10. Now I could go further, but I won't need to. Check it out. Taking an arrow, I can actually connect all the green lines together to give me a linear. Coincidence? Of course not. I've added a straight line with another straight line. It's like saying I have this blue line and I'm adding by the same, I guess, rate of change. Every single x value is increasing by a specific amount. So, or sorry, a consistently increasing amount. And so, yeah, you should have a linear. Okay. Yeah, that's what sum of a function is. I don't think this concept is particularly mind-blowing. It just makes sense once we hash it out together. All right. What is interesting, though, is when we talk about domains, which we will get to at a later point in this lesson. State the domain of each function. Well, for f of x, it's a linear, so I'm not even going to go into it. You should know that any x value works. Any real value works for x. For g of x, same thing. X belongs to any real numbers. So let me add squiggly lines, squiggly brackets rather, and we're done. Sketch h of x by visually adding the y values of the two functions in the graphs to the left. Does the line correspond to your equation in part C? Well, let's see. F of x is equal to 2x minus 1 plus g of x equals x plus 2. And if I were to group like terms, this becomes 3x plus 1. Let's check it out. I will use the color orange. My h of x says it is a linear function with the, with the form mx plus b. My y value should be a positive 1. Is that right? Yes, it is. I also know that my slope is supposed to be a 3. Now, even without calculating, does it look correct? Yes. How do I know? Well, I know f of x, this red line, is a 2. My green line is steeper than the 2. So even if I don't calculate it, I think I'm on point. All right, there's a way to confirm without actually calculating, just using ballpark numbers. Here we go. So I'm going to say, yes, it does. And you can confirm it by taking any 2 points, like maybe this point right here and that point right here, and calculating the slope, y2 minus y1 over x2 minus x1. Okay. We're going to do the exact same thing when I give you a parabola with a linear, and you'll see that it's still the same process. So any questions with this first example before we move on? Going once, going twice, going 3 times, going 4. All right, let's move on. Here we go. This time I give you a parabola, as you can see. And oh yeah, I actually made a small mistake in my previous class. I wrote a 3 there by accident, but it's supposed to be a -4. I'm glad I fixed it before this class. All right, next. Let's do it in order this time. I have x squared minus 4 as f of x. And clearly, this black line is my parabola, which means the other red line must be my linear. State the domain of each function. Again, using your grade 9 and 10 knowledge, you should know that the domain of a parabola is that x can be anything, any real number. Anything goes. Same with g, knowing that this is a normal linear equation, there's no restrictions. Let's move on. Define a new function, h of x, as a sum of f of x and g of x. So let's do that. F of x is the parabola plus g of x is x plus 1. I suppose I could have done a subtraction, but it's just a lot easier to understand this new concept as an addition for now. So this becomes x squared plus x minus 3. Right. Can this be? Oh, I made another mistake, everyone. Do you see this red line? That is a y-intercept at 2. This is supposed to be x plus 2. Sorry. So this is x plus 2. I really need to fix this, which means this is what I meant to do. Negative 4 plus 2 is a negative 2. Yes, this is what I meant. Why is this what I meant? It's because this is factorable, and when we add this, you will see a parabola that's easy to match with this. Let me explain. X squared plus x minus 2. If you factor it, you will get product sum, a positive 2 with a negative 1. Do the math. 2 times negative 1, negative 2. 2 minus 1, positive 1. It matches up. So in other words, if I were to add f of x and g of x, I should get a parabola, a quadratic, that has x-intercepts at negative 2 and an x-intercept at positive 1. Let's test it out. Here we go. Green. At negative 2, when the x value is negative 2, both y values are 0. So there it is. When x equals 0, I have 2 plus a negative 2. So, 2 plus a negative 4, that's negative 2. Jesse, I'm not sure what the question is. Could you clarify?
Yeah, on section C at the very bottom, it says x is equal to negative 2, x is equal to 1. And I'm just wondering the negative 2. Yeah, right there.
Well, it's the idea that if the y value was a 0, x would have to be a negative 2. The bracket is x plus 2, which means what if that bracket was equal to a 0? Well, then x would have to be a negative 2.
But isn't that a 1? In the bracket?
Oh, that's a 2. That's a 2. That's a 2.
Oh, okay.
Sorry. Plus 2. There. I'll try to do the loop so that it's a bit more clear. All right. Let's move on. Let's see. When x equals a 2, I have a 4 plus a 0. So I have 4. And then again, 3, 5. When x equals a 3, the y values for both functions are 5 or is 5. So we add the 5. So we have 10. And I could go further. Just to make my point, I'm going to add one more set of data here. I have on the g of x, I have a negative 1. And on the f of x, I have a 5. When you add 5 with negative 1 at this x value, I would get 4. So plug this data in. Oops. And try to draw the curve. I will get myself. It's not a very nice curve. See if I could do this. Ugh. Something like that, where the vertex will be approximately here at the negative 0.5 mark. Sorry, my curve is terrible. Let's see if I could redo that. So I know that my line of symmetry will be right there, giving me something like that. Okay. And it makes sense. Remember, my x-intercept was a negative 2. And from my calculations, my x-intercept would also be at a 1. So it sort of works. It's not the best drawing, but my answer here is also a yes. Does the graph match the equation? So what I'm trying to say is whether I do it manually or I do it algebraically, you will get the same thing. Another point that I want to mention is if I take this and I calculate the answer for the f of x, I calculate the answer for g of x. In other words, h of x is equal to y f plus y g, right? If I calculate the y value of each function independently, and then I add it together, I will get the same answer as if I was calculating the equation separately, like my new equation separately. Okay. The reason why I feel like I might sound like I'm beating a dead horse, right, is that there is a principle. If you look at the bottom or the top of the next page in underline, is something called a superposition principle. I want you to understand that again. I'll say it one more time. Whether I draw a new function, whether I create a new function with the components, or I solve the component separately and then I add it later, I'm always going to get the same result at the end. Okay. Kinda, you had a hand. What's up?
Would you be able to add the functions if they had different domains?
Oh, that's a very good question. Guess what I'm going to talk about after? The
Okay.
domain. Good question.
Okay.
No, that's awesome. Good for you. Okay. So what I'm trying to say is the superposition principle. If there is a sum of two or more functions, we can find the sum of two or more functions by adding the y values or the ordinate at every corresponding x value. So abscissa. Don't ask me what these words are and why they are still quoted in the textbook. You could think about it as when this superposition principle idea was first proposed and was accepted, you could imagine it was during dated times, and these particular words were mathematically correct. Right? So, and that definition has been carried through up until today. So the proper definition of the superposition principle, or the fact that the compounded, so the added function is equal to adding each piece independently, is that the sum of two or more functions can be found by adding the y value at each corresponding x value. So they're adding the ordinate at each abscissa. This principle can be extended, sorry for the spelling error, extended to the difference of two functions as well. So using the superposition principle, I am going to prove to you that this will be true whether I use the completely added function. So in other words, if I solve by using h of x, or if I solve by using g of x. But you will see that sometimes using the compound or using it separately will be easy. Sometimes you will see that doing this and solving for the final equation first is easy. Okay. So let's start with the easy mode, or the hard mode, at least for this question. It's not always the case, but in this particular case, yes, h of x will be a little harder. H of x is going to be the sum of these two functions, which means I need to solve for the sum of that. And yes, I'm being a little extra, but deal with it. How do you add fractions? Well, you need the same denominator. This is x squared minus 3, x minus 2 over x minus 2 minus a 6. So the numerator becomes x cubed minus 2x, x squared, sorry, minus 2x squared minus 3x, and then plus 6 minus 6. And there we go. Following, the question asks for what is the value of the function when x equals 4? So 4 times 4 times 4, 64. 4 times 4 times a negative 2 is 32. 4 times negative 3, that's a negative 12. All over 4 minus 2, I'm going to solve that, that's a 2. So this is 64 minus 32 is a 32 minus 12 is a 20. 20 divided by 2 is a 10. And there you have it. Right? Following. Dun, 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 dun. What if I solved it separately? H of x is supposed to be f of x plus g of x. And by superposition principle, I can technically say that h of 4 is the same as plugging in a 4 to each of its components. Oops. Right? You can add the y value of each corresponding x value of these two functions. They're one and the same. And so what is f of 4? That would be 4 times 4 minus a 3. So 4 times 4, 16 minus a 3, that's 13. And g, what is negative 6 divided by 4 minus, that's a 2. That's a negative 3. 10. Ta-da! Therefore, 4 comma 10. One and the same. Okay. Next, talk a little bit about domains. But before I get there, any questions?
I got one about the first two examples. I know it's a little late, but I figured I'd get it out.
Sure.
So when you were adding the y coordinates or the y values to find the y value of the new lines, how did you know which ones to add? Like, I assume it was like the furthest ones to the left on one line with the same one, but wouldn't that mean that every line, like every question you give us would have like a certain amount of coordinates to add? If you want, I can rephrase it. I don't know that I explained it great.
Yeah, I'm not sure what your the
So-
main example is, but let me try to explain. I think I get it.
Okay.
I'll clear this. What I was adding is the corresponding x values for every single point. So when x equals negative 2, on the blue line, I have a y value of 0. When x equals negative 2, on the red line, I have a value of negative 5. And so I was adding 0 with negative 5 to see what my remaining y value was.
Okay, so it wasn't like, so the only reason that they were happened to be that same order is because the x coordinates were the same.
Correct. Because remember,
Right.
they were asking for the sum of f of x and g of x. What is f of x? Another way you can say f of x is the y value, right? Same with g. What's the y value of g? Another way of saying, what's the y value when x equals 2? And what's the y value when g equals 2? That's why I'm adding these two values together. Or, sorry, negative 2, negative 2. Okay?
Yeah. And on the quest, I assume, like, if you give us a question like this, you'll give us the same, like the coordinates that are given, they'll all have the same x value then.
Or it wouldn't make sense to add any other y values other than the corresponding x's.
Okay then. All right. Okay, thanks.
No problem. Determine the domain. So domain, take a look at this function, right? The combined function when I added it together. What would be my domain? Well, from the looks of it, there aren't going to be any like vertical or horizontal asymptotes or whatnot. Oh, sorry, except one. There's going to be something in the denominator, but I don't see anything restricting this function other than the denominator. So in this case, you would say that x belongs to real numbers, but x cannot be a 2 because, the denominator would be a 0. Okay. Let's compare that domain for f of x. For f of x, it's just a parabola. So for f of x, that's going to be a real number. For g of x, I have a fraction. It's a reciprocal function, reciprocal. And if you remember anything about reciprocals, well, it could be any real number except the denominator cannot be 0. So let's compare domain, domain with domain. Loosely, I will say that f of x could be anything. G of x is more restrictive. And so between those two, the domain has to be the one that has more conditions, is more restrictive. Okay. Just because I combine it doesn't mean you say, hey, we combined it, so let's remove the x cannot be 2. It just doesn't, no, it's still there, right? And it makes sense if you think about it graphically. If you can't, f of x provides a value when x equals 2, but g of x, it's not existent. It does not exist. And so there's nothing that we can add. Another example, let's pretend f of x, when x equals 2, when f of 2, that equals 1. G of 2 is not a 0, right? It's not like when you're adding it together, it's not like h of x is saying 1 plus 0. 0 is a number. G of 2 is not existent. It's undefined. In other words, it's not 1 plus a 0. It's actually 1 plus not existent, which is not a mathematical statement. You can't add that correctly. This is why when you compare domains, we go to our next section. The domain of a sum or difference of functions is the domain that is common to all the components. Everything else, the restrictions come down. You cannot add values that do not exist. So here's an example. I'm not giving you a function here. I'm actually giving you a thing. Quality of life question. When I'm talking, does my voice occasionally like buzz? Because I'm hearing some weird feedback on my own headphones. No, okay, it's just my voice. Okay, so I'm going crazy. Great, I love that. All right, here we go. So taking a look very simply, I'm going to approach this in a very elementary way. What are some x values that are common? Well, so let's do it in a nice, acceptable, happy green color. -1, -1. 0, 0. 1, 1. 2, 2. And 3, 3. What are the x values that are not common? -3 doesn't exist here, so we cannot have that exist in our new joined function. -2 cannot exist. +4 cannot exist. When I determine f plus g of x, new notation, new. New flavor kind of thing. When you add, you can only add the common x values. And how am I adding it? The x values aren't adding. Remember, when we're adding it, it's like y plus y, we're adding the y values. So this is -1, 14 plus 4, that's an 18. 7 plus 5, that's a 12. 4 plus 6, that's a 10. 5 plus 1, that's a 6. And 7 plus -16, that's a -9. What is the domain? Well, it could be -1, 0, 1, 2, or 3. If you want to be a little extra or want to flex your muscles a little bit, you would say that x belongs to any integer between -1 and 3. That's another way you can write it. or there. X is an element of integers such that -1 is, X is greater than -1 or greater than or equal to -1, but less than or equal to 3. Same with the range. Range is a little bit funky. Range could be from -9 and then 6 and then 10 and then 12 and 18. Okay. The same is going to be said for determining subtraction. Let's go through this very, very quickly. I'm just going to write out what the function would be, and I think you can determine the domain and range by yourself. Even when you're doing subtraction, it is the same. You are taking the y value of f and you're subtracting with the y value of g. Please note that the order is important. F minus g is not the same as g minus f when we're talking about a function. So order is super important. So again, we can only add the common x value. So 14 minus 4 is a 10. 7 minus 5 is a 2. 4 minus 6 is a -2. 5 minus 1 is a 4. And 7 minus a -6 is 23. And I think you could do the domain and range by yourself. Let's see, yeah. That's essentially it. Literally, that's pretty much it for today. I am going to go through some of the more visual graphical questions. And of course, the very last question is going to be a little harder. But again, I just want you to grasp the idea. Foundationally, this is, I think, quite digestible. So I'm going to try to throw some harder questions at you so that you would be more ready for the quest that's coming up.
Hey, Mr. Kim.
Yes.
So for your first domain that you did, you had the x is of all integers negative, like it has to be greater than or equal to -1 and less than or equal to 3. But on the answer sheet, you didn't write that and you didn't do it in the next one. Do we have to write that down as well, or can we just do the x values?
No.
Okay.
Again, it's sort of like, it's just a preference, I guess. They
So
both
it's
mean
just
the same
either
thing.
or. Okay.
Of course.
Okay then.
It's like, it's the difference between saying, can I say I love pizza in capitals versus I adore pizza? Like it's, it's like, it means the same thing. Again, it's a language. Here we go. What does this look like graphically? Well, I think you ought to be able to figure it out, but just in case, let's do this. F of x is blue, g of x is red, but notice how f of x sort of stops abruptly at -4, whereas g of x continues on. By definition, the domain must be common for both, right? So it's not that g of x loses it, but I'm doing this so that you remember h of x does not have this portion, right? Because none in f of x. So let's do it. You might need a little bit of space, and if you have a different color pen, go for it. I will continue to use green. 3 plus -3, 0. 2 plus a -2, 0. 1 plus a -1, 0. 1 plus a -1, 0. 0 plus a -2, 0. -1 plus a -2, -3. -2 plus a -3, -5. And -3 plus a -5 is going to be -8, somewhere there. So if I were to draw a line going through, it would be from here, and down, slightly less steep, steep again, and steeper. There it is. Try the next one. I'll give you 2 minutes. For this one, I'm just going to do F minus G. I feel like you can definitely do the other one on your own. Something I do want to point out, though, a couple of things you can do to help your drawing. Because both lines are linear, you will see that your result will also be linear. Okay, so all you really have to do is draw some of the more key points and connect the dots with straight lines. You'll see what I mean right here. Here we go. 6 minus a 0 will give me a 6. I don't know what point that is, but they are the same y values. So they are going to subtract and give me a 0. Next. Oh. Wait. Sorry. I made a mistake. It's f minus 0, f minus g. So it's actually 0 minus 6. I have to start with -6. And then this portion means 0. Next. 4 minus a 0 means this is my next point. And then f and g have the same y value here, so I know I'm going to be going downwards. And since the trend for the black line and the trend for the red line aren't changing, I know it's going to continue on like that. So my f minus g will be, how about I draw straight lines here? There, straight line, and then straight line. This is my f minus g of x. Okay. And again, I'm not gonna, again, I really feel you can do g minus f as an exercise. You can also check my answer here, I suppose. I'm gonna move on for the sake of the video too. Here is where it can be a little bit funky, and I'm sort of excited to show you because, you'll be challenged, I think. What is the algebraic definition of an even and odd function? It's going to be a good refresher. Anyone remember what even and odd functions mean and how you can define it algebraically? I'll give you a hint. An even function is defined as something here. F of x is equal to something. Going once. Going twice. Well, what does an even function mean? A whole number that is divisible by 2, x to the power of an even exponent. Well, yeah, x is to the power of an even exponent, but visually speaking, how about I remind you of this? This is an even function. This is an odd function. This is an even function. This is an odd function. This is an even function. Um, uh, um, that is an odd function. Sort of. Sort of. I mean, yes, you're right, but in itself, there could be more to it, right? I think what Jesse and Joseph are both saying is just power functions. It's more simplified. What I was looking for is the fact that for even functions, there is a line symmetry, and for odd functions, there is a point symmetry. And what does that mean? For even, so this is even, it always has to be that. In other words, whether I have an x value that's a positive or I have an x value that's a negative, they're going to be perfectly equally to each other in terms of y values. And for odd, definition is, if I take a function and I plug in, or if I do a vertical reflection, it will be the same if I took that function and I did a horizontal reflection. In other words, that's going to be point symmetry. That's that. And so here is a bit of an extend question. I don't expect everyone to understand or to actually answer this at this point in time because you just sort of approach this idea. But let's pretend f of x and g of x are both even. I didn't tell you the shape. I just said they were both even. If I added them together, would the resulting function be even? Would it be odd? Or would it be neither? And so is this some kind of mathematically like mind-blowing concept? Not necessarily, but it could be of use when you, I guess, I don't know, continue on with certain things in the future. Let me explain a proof to show what it be. The answer would be even, correct. But more than saying it intuitively, it's best to prove. And notice how I am going to prove this without any case examples. I mean, I could say, oh, f of x is even, and then f of g of x is even. So yeah, x plus 4 plus x plus 2, look, the odds are, the exponents are even, so it has to be even. That's not enough. If you want to prove by cases, you have to prove with every single case in the world, which is infinite. It's too difficult. Here is my proof. Given, let's pretend that I have h of x is equal to this plus that. Okay. So would f plus g of x be even, odd, or neither? Is h of x going to be even, odd, or neither? So if this was in fact even, what would it be? Well, let's pretend. Let's pretend we do plug in a negative x into the equation. Well, by superposition principle, what does that mean for the entire function? Well, if the x value for h is negative x, then the x value for f is negative x. The x value for g is negative x. But what do we just say that f and g are? They're both even. So what does that mean? If I have f of negative x, I could rewrite it as f of x. And if g of negative x is even, I could say it's the same value as g of x. And all of a sudden, I have shown that whether I plug in negative x or whether I plug in a positive x, I get the same function. Therefore, the resulting sum of the functions is also going to be an even function. Okay. Any questions so far? With that said, I don't think you have too many questions, but with that said, what would you predict this one to be? I have two different odd functions and they're going to be added. So visually speaking, I have something that has point symmetry and I have something that has point symmetry. If I were to add it together, what do you think would happen? Going once, going twice, one person, odd. I would agree. It makes sense. So I have something that's increasing like this, but I am adding something that goes like this. So if you've done physics, they're superpositioning. So they're adding together going to be like something like that. And the same will be applied to the negatives because a negative plus a negative becomes a larger negative. I still think we're going to get an odd function, but it's not enough to speculate. We have to prove it algebraically. So let's give it a shot. If we were in class, I would probably give you like a minute to try, but it might be complicated. So again, let's define h of x to be f of x plus g of x. Now I'm going to test both. I have to test when I plug in a negative or I multiply the entire function with negative, and then I have to test if I plug in a negative x into the function. Okay, let's do the first one. If I multiply the entire h function with a negative, that is like multiplying all of the components with a negative. Okay, and I'm going to multiply it out. That would be a negative f minus a negative g. It's like -1 multiplying to both functions. There it is. All right, let's move on. Next, I have a negative x plugged into the function. And by superposition principle, that is the same as this and that. Now, clearly, these two don't look alike. But remember, I've already stated that f of x and g of x are both odd, which means if I have a function that has a negative x value, it will be the same as having a function with a positive x, but a vertical reflection instead. So I can rewrite this as negative f of x. And the same applies to g. That's a negative g of x. And all of a sudden, I'll do it in red, negative h of x is the same as h of negative x. So algebraically, I have proven negative this is the same as this. So it is odd. Without any case examples, I proved it algebraically. And that's important to do. And now that we know this, we could use it to our advantage and do whatever we want. Any questions? I don't think there would be, to be honest. It's just sort of like, oh, that's cool kind of thing. I'd like you to still be responsible in trying some of these questions. If you take a look at number 4, I threw in a cosine and as well as a weird linear. Let me bring this down. Okay. If you're still copying, I'll save it. Don't worry. Okay. But if you take a look, I am asking for an addition of these two functions, a subtraction of these two functions, and then a subtraction in the reverse order. How you would go about it is literally just adding the y values, because there is no real simple way to add or subtract these and give me a condensed, simplified equation for it. Like, what the heck does this simplify to, right? Nothing. So the whole point of number 4 was take the y value here, take the y value here, add it or subtract it. Take the y value here, take the y value here, add it or subtract it, and so on and so forth. And you'll get yourself a very funky looking, like, graph. Yeah, if you notice, they're both, oh, I can't say it's even or odd, and never mind. Yeah, you'll get some funky patterns from it. It's just an exercise to help you practice manually adding or subtracting graphs. I also have a couple of questions I believe you can use from the textbook. They're relatively simple, and once you get the hang of it, you'll start getting tired and be like, I know all this stuff, I'm going to skip. No problem. But make sure you're responsible and you try a couple of these questions. There. There. Okay. All right. Any questions? All right, then here's what I propose. Again, I don't need to go really in depth into 8.2 because it's exactly the same stuff, but multiplication. So you could imagine multiplication and division. It opens up a couple of more doors, a couple more layers you need to think about as you're calculating. But in terms of the, I guess, the math, the mechanical portion of it, the actual calculation portion of it, it's nothing new. So instead, I'd rather you sort of think about what's to come by practicing some of these textbook questions. You are also free to work on your culminating, because based on the number of people who've responded so far, I don't remember seeing too many people say that they're going, if anyone, actually. I don't think I remember this class. I checked it yesterday. I don't remember anyone saying they don't want to do the activity. I think everyone here wants to do the activity so far. So let's go to our whiteboard. A couple of things I'd like you to do today. To do now. We're going to break. Number 2, meanwhile, please do survey. I've only gotten 14 people responded. Okay, and number 3, we will intro 8.2, and then the rest will be, I will create breakout rooms so you can work on culminating in groups. Okay, so let me give you a 10-minute break, and while you do the survey, and then we'll finish off 8.2 really quick, just an idea. We're not going to do the entire the lesson, and then the rest of class is for us to work on the culminating together.